Well, that was uncomfortable. Welcome back. Let's see if we can make this go a little better. So I've got dots. Okay. So whenever y is equal to 0, I have dividing by 0, which is an infinite slope. And that happens here, here, and here. When x is equal to 0, now I'm going to have a horizontal slope. What about at 1, 1? 1 over 1, I get a negative 1 slope. In fact, if I come over here to 2, 2, negative 2 over positive 2, that's still a negative 1 slope. In fact, I have that everywhere along this diagonal. Okay, so how about here, 1, 2. 1, 2 is negative 1/2. So this was 0, this was minus 1, and this is in between. And here, 2, 1, that's negative 2. It's even steeper than that one. Here at 1, negative 1, 1 here, and a negative 1 here, I have a slope of negative 1. What about here at 2, negative 2? 2, negative 2. Oh, it's not a negative 1. It's a positive 1. There we go. Because that negative and that other negative from the x value here cancel and give me a positive. And I can run these back up here as well. So if I plug in a negative 1 for x and a positive 1 for y, I still get a slope of 1. So slope of 1, slope of 1. Here I have 1, negative 2. 1, negative 2, that's a positive 1/2 slope. Here I have negative 1, negative 2, negative 1 times this over negative 2. That's going to be a negative slope on negative 1/2. And this one will be negative 2. What about here? 2, 1. 2, oh, negative 2, positive 1. It's going to be 2 over 1 or 2, very steep. And this one turns out to be 1/2. And so there's my slope field. Okay, that's part A. The antiderivative, yeah, looks like a bunch of concentric circles. And that's what I would expect because this differential equation becomes the equation for a circle. Number 2, solve the initial value problem given this. Let's see. And so then I get y equals x squared plus c. We've been given an initial condition to use. F of 0 equals negative 1. And so we know that c is negative 1. And so our equation is y equals x squared minus 1. Then we're told to show the solution on dy dx's slope field. Okay, so let's make a slope field for dy dx. All right, so we know that dy dx is 2x. So if I put an x value of 0 in, dy dx is 0. So horizontal slope. If I plug in a 1, well, 1 times 2 is 2. Regardless of what the y value is, the x is, whenever the x is equal to 1, my slope, my dy dx will be 2. How about 2? 2 times 2 is 4. Oh, much steeper. And here, negative 1. Negative 1 times 2 is negative 2. And this one would be negative 4. And we're supposed to put our particular solution on this. Well, there's our particular solution. And so we're looking for something that looks like that. Okay? All right. Yes, why that is. From 2x, we see an infinite number of parabolas stacked together there. So yay, we're done with that. Okay, next. Station number 4. So station number 4 tells me to use u subs to determine each antiderivative. Oh yeah, please. I mean, really, you should really be doing these problems before I start doing them. Maybe you should do all of the stations and then come here and check. This is a u sub. I see a function, and I see the derivative of that function. So if u equals x plus e to the x, du will be 1 plus e to the x dx. And there it is. So this becomes 1 over square root of u du. And you know that I prefer to write that as u to the minus 1/2 du. So my antiderivative here, u to the positive 1/2. Then don't forget I need that 2 here. So when the 1/2 comes down, they cancel. Don't forget the plus c. And we need to back substitute. So 2 x plus e to the x to the 1/2 plus c. You can leave your answer like that or go back to old school radical. Either one of these is fine. Okay. All right, number 2. So I've got the integral of x, 1 plus x squared dx. Again, I see a function, and I see part of the derivative of that function. So if u equals 1 plus x squared, then du is 2x dx. I have an x dx, so there's an x dx, and I can replace with du over 2. So now I'm going to have 1 over u times du over 2, or 1/2 integral 1 over u du, which is ln of u plus c. So now I've got 1/2 ln of 1 plus x squared plus c. Okay, next we've got the integral of 1 over x squared plus 4 dx. Well, I hope your brain is saying, hey, that's going to be inverse tangent. So how do we get it to be inverse tangent? Well, I'm going to simultaneously divide the stuff in the bottom by 4, as well as multiply by 4. So that gets me to this. And remember, my u is going to be the square root of each of these things. So u is x over 2. U is x over 2. So this can now be written as 1/4 integral 1 over u squared plus 1. Yeah, because if I square these, I get this. And if I square this side, I have to square that side. That's why that's u squared there. Du, let's think about that for a second. So if our u was x over 2, wouldn't our du be 1/2 dx? So that's going to be 2 du equals dx. So to get rid of this, I needed that times 2 du. Okay. So this 2 comes out, 2 over 4. I have 1/2 integral 1 over u squared plus 1 du, or 1/2 tangent inverse u plus c. Don't leave here. Keep going. Our answer is 1/2 tangent inverse. What did we say our u was? We said x over 2. All right. That's station 4. How about station 5? Use tabular to determine the antiderivative. Well, that's great. Who doesn't like tabular? X squared sine x dx. Okay, so we've got x squared, we've got 2x, 2 and 0. Remember, these are antiderivatives. Whose derivative is this? Your negative cosine's derivative. Whose derivative is this? Why, that's negative sine's derivative. Whose derivative is this? Cosine. And then on the diagonal, don't lose that or that. All right, so this times this, negative x squared cosine x, plus this times this, minus 2x sine x, plus this times this, and don't forget the plus c. What else did we forget? Right, we have to multiply this and this and this by a thing. So we multiply here by a positive, by a negative, by a positive. So the sign is not changing on this one. The sign is not changing on this one, but the sign is changing on this one. All right. How can we check? Well, if I take the derivative of this, including product rule and product rule, and combine like terms, I should end up here. Okay? You might want to try that out. All right, here's our next one. Integral of x squared e to the x dx. All right, so I think I'm going to do it the same way. X squared 2x to 0, and just a bunch of e to the x's. Times positive, times negative, times positive. And so we're going to have x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Yeah, that looks good to me. Hey, let's change this problem a little. How about if I had 3x here? How would this problem be different? I still want to use tabular. Some people write this. Is that correct? Well, no. That's the derivative. I want the antiderivative here. Well, that's a great start. But if I take the derivative of this, I get e to the 3x times the derivative of the inside 3. I don't see a 3 here. So there must be something present on this original function here that when I take the derivative of that inside, and there should be a 3, there is no 3. And the thing that I'm missing is not times 3, but over 3. And every time I go back again, there's going to be an additional 3. So e to the 3x over 9 and e to the 3x over 27. So then we're going to have x squared over 2, x squared over 3 e to the 3x minus 2x e to the 3x over 9 plus 2 over 27 e to the 3x, and don't forget the plus c. And again, to check, if you take the derivative here, you should end up with this when you're done combining like terms. Each time. All right, number 3. Do you recognize this one? Kind of hope you do. This is the one that spins forever. This goes forever, this goes forever. I want to do by parts. So I'm thinking, well, okay, we'll do this by parts. X, dx, dx, negative sine x, dx, and e to the x. So I'm going to have e to the x cosine x minus the integral of e to the x negative sine x dx. Well, that negative comes out with that negative, and I get myself a positive. So now I'm saying the integral of e to the x cosine x dx equals e to the x cosine x minus times minus is plus e to the x sine x. Okay, well, one more time. No, it's always twice. I promise. Always twice. So I put tricky here before. I'm going to put tricky here now. And exponential here. This is e to the x. And this is going to be cosine x dx. So that e to the x cosine x dx equals e to the x cosine x plus e to the x sine x minus this times this e to the x cosine x dx. Well, that's great, because that is where we started. So now I'm going to add this to both sides. And I get one of them plus one of them makes two of them. Exactly. 2. And these cancel. So now I've got this, but I don't want to know what 2 of these integrals is. I just want to know what one of them is. So I'm going to divide both sides by 2. And that's my answer. This integral is equal to this. Of course, you could factor out that GCF stuff and be left with that. And that was the last one there. Yep, station 6. Okay, use by parts. X over e to the x dx. And you know, I feel like I really would prefer to write this without the fraction. These problems are generally much easier when I don't introduce a fraction as well. Well, I want to put my x there, because I know that's just going to be 1 dx. Here I have e to the minus x. And when I take the antiderivative, yeah, I like e to the minus x. However, if I take the derivative of e to the minus x, don't I have to take the derivative of that inside function? I don't see a minus here, so there must be something present on the original function. So when I take the derivative of that inside and the minus comes out, minus times minus gives me the positive that I'm looking for. Okay, so we've got negative x e to the minus x minus the integral of negative e to the minus x dx. Right, this times this is here, minus the integral of this times this. Well, minus times minus is plus. And now what can we do? Well, I know that the antiderivative of that is minus e to the minus x. And this is all set. Minus x e to the minus x. And don't forget the plus c. Again, if you're not sure, take the derivative. Take the derivative of this with product rule, take the derivative of this, combine like terms, and you should end up here or here. Derivative of a constant, 0, so you certainly don't have to worry about that. Okay, that's the first one on station 6. How about the second one? Y over square root of minus y dy. And we're directed to consider using a u sub here. So let's take a look. Yeah, that's kind of screaming u sub to me. And if I take the derivative of both sides, so here's y. Y is this. Here's dy. dy is this. So I've got 1 over square root of y times y. Sorry, square root of u. And then the dy can be replaced with negative du. All right, and take the negative out. And so now I've got negative integral 5 minus u, square root of u du. And this can be split up into two integrals. Minus du. Okay. And that takes me to negative 5u minus 1/2 plus integral u times u to the minus 1/2 du. So my antiderivative here, 5u to the 1/2. Oh, but when I bring down the 1/2, there's no 1/2 here, so there must be a times 2. So that 1/2 comes down, 2 and the 1/2 cancel, leaving me that 5. You don't lose that. Plus, I'm multiplying, and the bases are the same, so I can add the exponents. It's going to be the integral of u to the 1/2. The antiderivative there would be 2/3 u to the 3/2 plus c. All right, well, almost done. We just need to plug back in here. What was it that we said we would use for u? We said our u would be 5 minus y. So I've got negative 10 square root of 5 minus y plus 2/3 5 minus y to the 3/2 plus c. Okay. Okay. Now, what about this last one? This last one. We've got the integral sine inverse of x dx. Well, I know how to take the derivative of that, but do I know how to take the integral of that? No. That's what I'm starting with. And so what's left for here? Only 1 dx. So this thing that I really didn't know how to integrate by parts. I can turn that into x sine inverse x minus integral x over square root minus x squared dx. Now what about here? How do I take this derivative? This antiderivative. Well, let's say u sub. Oh, okay. So that's going to be the integral of 1 over square root of u times du over negative 2, because that's what x dx is. Okay. I think I would prefer to write this as u to the minus 1/2, and a negative times a negative is going to give me a positive 1/2. Hey, what's the antiderivative of that? Yeah, I agree. That's going to be u to the 1/2. If I bring that 1/2 down, oh, there it is. And so we've got x sine inverse x. And no, I can't stop here. I can't have both x's and u's in my final answer. So because I see this u here, I'm going to replace with what u is equal to. So we get x sine inverse x plus square root 1 minus x squared, and don't forget the plus c. All right? All right. Really, it's just practice. Just practice, 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 practice some more. Hey, look, another slope field problem. This time dy dx equals y minus 1. Okay. So, there's no place for x's here, there's just y's. If I plug in y equal to 0, I get dy dx is negative 1. So here's y equals 0. If I put in y equals negative 1, I get negative 1 minus 1 is negative 2, so that's a little steeper. And then if I plug in a negative 3, no, a negative 2, that's going to be a slope of negative 3, which is steeper still. And if I plug in a 1, 1 minus 1 is 0. If I plug in a 2, 2 minus 1 is 1. And so if I had one more, they'd be steeper still. And so ideally, I see something that could kind of look like, yeah, I'm not going to say. Okay, so question 2. Solve the initial value problem, dy dx equals xy, given that f of 0 equals negative 1. And then draw the solution on the slope field. All right, well, let's start by separation of variables. dy over y equals x dx. I integrate both sides. And, if you're a little stuck over here, I think this might help. Right, because now I'm looking at, oh, that's ln of y. As opposed to here, maybe it was a little harder to see. So we're going to have ln of y equals the antiderivative here, x squared over 2. I now need to exponentiate. Times e to the x squared over 2. And if I get rid of that absolute value, I have something that looks like this. Okay, so we had that initial condition, 0, 1. Oh, I want to do something here like a equals plus and minus e to c. So now my model is a, e, the x squared over 2. And if I plug in that ordered pair, 0, 1, well, 0 divided by 2 is still 0, and e to the 0 is 1, and 1 times a is still a, and so a equals 1. So y equals e to the x squared over 2. That's my answer. And don't circle your answers. I need to draw the slope field. Okay, let's draw the slope field. So we know that dy dx equals xy. Okay. All right, so if x equals 0, then 0 times stuff is still 0. Oops. And if y equals 0, 0 times stuff is 0. And what about 0 times 0? Well, that's a big old 0. So that's an interesting start. How about here at 1, 1? 1 times 1 is 1. 2 times 2 is 4. 2 times 1 is 2. And 1 times 2 is also 2. Negative 1 times 1 is negative 1. And negative 1 times 2 is negative 2. Negative 2 times 2 is negative 4. And here negative 2, 1. Negative 2 is this one again. Okay. But wait, there's more down here. So if I plug in negative 1, that gives me a positive 1. And if I put in negative 2, I end up with positive 4. Here, negative 2, negative 1, positive 2. So it's a little less steep, that's a little more steep, and that's steeper still. And the slope is going to be the same because we have a negative 1 and a negative 2. And finally over here we have positive x's but negative y's. So we'll see something like that. And something like that. Something a little steeper than that, but not as steep as that. There you go. Kind of looks like a big spider, doesn't it? Or how about a bunch of parabolas and then a bunch of parabolas? That's interesting. And yet we know this is going to become some sort of e to the x kind of thing. Okay. Station 8. Solve the initial value problem. dy dx equals cosine x minus sin x and y of pi equals 1. Okay, so we know that dy equals cosine x minus sin x dx, and I integrate both sides. I get y equals sin x plus cosine x plus c. Please don't forget, this is someone's derivative. Whose derivative? Sine's derivative. Many students look at this and they say, oh, the derivative of cosine is negative sine. Yeah, no, that's not our problem. This is going backwards. This is someone's derivative, and that person is sine. If I take the derivative of sine, I get that cosine. If I thought negative sine, the derivative of negative sine is now positive cosine. Okay. Anything else? Oh, initial condition. 1 equals sine of pi plus cosine of pi plus c. Sine of pi is 0. Cosine of pi is minus 1. And so it looks like c equals 2. So you're not done until you replace. That's our function. Don't box in your answers. Hey, what about number 2? Here we're told that dy dx is equal to 1 over x squared plus x, and that y of 2 equals 1. Okay, so separation of variables. I'm just going to write that as x to the minus 2. And now when I integrate both sides, here I'll have y, and here I'll have negative x to the minus 1, right? Bring that down, minus times minus is positive, subtract 1, good job. And this is plus x squared over 2. And don't forget the plus c. So now I'm going to plug this in for x and this in for y. Okay, so 4 halves minus 1 half is 3 halves. 2 halves minus 3 halves is negative 1 half, so c is negative 1 half. And we can plug back in here. And there's our antiderivative, our particular solution to the situation. Okay. Oh, second derivative for number 3. Two minus 6x dx and integrate. It may be helpful here to write this like this. Yeah, because one of them went over there. I'm not quite happy over there, so let's look over here first. 3x squared plus c, and here I have dy dx, right? Because the integral, yeah, I don't know. Justin, we know that y of 0 equals -3, and y prime of 0 equals 0. So y prime is dy dx. I put in the 0 for x's, I put in the 0 for dy dx, end up that 0 equals 0 minus 0 plus c, so c equals 0. Great, so that goes away. Now I need to do separation of variables again and integrate both sides. So I get y equals x squared minus x to the third plus c. And this time we plug in that second ordered pair, namely that y of 0 equals -3. So -3 equals 0 minus 0 plus c. I guess c is equal to -3. And there's our specific solution. And that was station 8. How about station 9? Integral x cosine x dx. Okay, so the directions here say find the indefinite integral in each case. We're not given any hints. What kind do you think this is? That's right. It's by parts because I see someone and someone else's derivative. Okay, I'm going to put my x here, put my cosine x here. My antiderivative is going to be sin x. So, using by parts, I have this times this, minus the integral of this times this. What's the antiderivative here? Well, the antiderivative of negative sine is positive cosine. And that's as far as we needed to go. It was not an initial condition problem. And again, if I take the derivative of this, I should end up here. No, really. You want to see? Let's go. So, product rule. X times cosine x plus 1 times, the derivative of this is cosine x, right? I take the derivative of that, so I should just have a sine x here. And the derivative of cosine is minus sine, and the derivative of a constant is 0. Oh, look. These combine and cancel, and what am I left with? There it is. So yeah, you know you've done it right when you can take the derivative of what you think the antiderivative is and show that, yeah, it works. Ooh, what about this one? I remember that we did tangent as a u sub where u was cosine x. But this problem is saying inverse tangent of x dx. Well, that's by parts. I know how to take that derivative, so I'm going to put that there. 1 over x squared plus 1. And I got just 1 dx left over. So that's going to be x. So this integral then is x tangent inverse x minus the integral of this over that. So how am I going to take that integral? Well, that's good that you noticed. That's right. The derivative of this is going to be 2x dx, and I got a lot of it here. So if u equals x squared plus 1, du would be 2x dx. du over 2 is x dx. So that is du over 2. And here I have x squared plus 1 as my u. So this is going to be minus 1 over u du over 2. All right, well, I'll pull out that, and I'll have a 1/2 here. And the antiderivative of 1 over u Yeah, it is ln now and again, but not always. So we've got x tangent inverse x minus 1/2 ln of u plus c. Okay. And weren't we given an initial condition? No, we were not. So there's my answer. Oh, no, it isn't. No, it isn't. Let's see. Y parentheses x squared plus 1 is never negative. It's a parabola shifted up one. It certainly looks like by parts, function and someone else's derivative. But really, yeah, I'm sorry. No. I FOIL. And then I just do the antiderivative. And the directions didn't specify means. So those are my means. Station 10. Integral x to the third sin x dx. Well, a function and someone else's derivative, a function and someone else's derivative. I'm thinking by parts. Whoa, no. I don't want to do by parts 3 or 4 times. So let's use tabular. X to the third, 3x squared, 6x, 6, 0. Here we've got sine x, not the derivative. I need the antiderivative of this. Negative cosine x. And the antiderivative of that. And the antiderivative of that. And the antiderivative of that. Plus, minus, plus, minus. Okay, so I'm going to end up then with x to the third sine x. Negative times negative is positive. 3x squared sine x. Sorry, that was a cosine. And there was a negative here, but no negative here, so don't use that. That one was positive. And then I have plus 6x cosine x. And then here, minus 6 sine x. And don't forget the plus c. All right. Go tabular. B, 10b, the integral of x squared minus 5x times e to the x dx. Well, I see a function and someone else's derivative, or I see a function and someone else's derivative. So I'm going to use by parts here. Oops. Okay, so this times that. Minus the integral of this times that. Don't forget the plus c. No, because I still have an integral. Okay, what next? Well, hey look, same. Let's do it again. We have 2x minus, 2x minus 5. This is 2dx. This is e to the x and e to the x. Remember, all the stuff that we do from here is behind this minus sign. So, I'm going to put it there as a reminder. this times this minus the integral of this times this. Well, let's distribute that negative sign. And now here, I should be able to do that antiderivative. And there we go. I would say that there's some value in doing the distributing and combining like terms. And that's certainly what I would see if I were doing the multiple choice portion of the AP exam. And when I did that, I ended up with x squared e to the x minus 7x e to the x plus 7 e to the x plus c. When you distribute and combine like terms, I believe you should end up with it. Okay, that was it for station 10. Let's take a look at station 11. Looks like USEB country. Integral cosine square root of x over square root of x dx. So, what's my u here? That is. How come? Well, if u equals x to the 1/2, then du equals 1/2 x to the minus 1/2 dx. And that's the same as 1 over 2 square root of x dx. Well, if I put my finger over the 2, that's what all that stuff is. Now, I really want this by itself, so even though there's that 2 here, I think I want to multiply both sides by 2. So, all of this can be replaced with 2 du. So now I'm going to have cosine u times 2 du, or 2 integral cosine u du. Okay, cosine of u, whose derivative is that? That's sine's derivative. And no initial condition, but we do want to get rid of our u. Our u was x to the 1/2 power. All right, there's my antiderivative. Woohoo! Okay, let's take a look at problem number 2. What's your USEB there going to be? You know, I like taking all of that. So, I've got a y dy, divide both sides by 2. So this can be 1 over u times du over 2. Nice. Okay, last one for station 11. What's it looking like? Integral x plus 1 over squared plus 2x plus 19 dx. So, what can we say here? What do we know here? So I can get rid of all of this with du over 2. Okay. Station 11 is all set. How about station 12? Integral sine of 5 theta to the 6th cosine of 5 theta d theta. Well, that is inside that function. So that is my u. So du is going to be the derivative of sine is cosine, leave the inside alone, times the derivative of the inside. D theta. Okay, now let's integrate both sides. I have u, both sides. No, sorry, not integrating both sides. I am replacing stuff up here. So this becomes u to the 6th, and cosine 5 theta because when I take the derivative there, the 5 is going to come out, it will need to cancel. And so I'm going to just move it over here. So 5. Okay. So that's going to be 5 times 7 e to the 7th. No. Yes. And so that's going to be 5 sevenths sine 5 theta cosine 5 theta. Okay, last one on. Oh, you almost let me forget the plus c. Why do I feel like that's wrong? It is wrong. I didn't have to the 7th. I had the over 7, but I left out to the 7th. Okay. Last one on 12. I swear we did this one right. So that's what I've got. So that can become 2 du. So this is going to be e to the u, 2 du, or 2 e to the u, du. So the antiderivative of e to the u is e to the u. E to the u, 2, and our u was square root. So 2 e to the square root of 1 plus c. All right. Just practice. Just practice, practice, practice. And of course, don't forget to check your answers to make sure you're practicing correctly. You wouldn't want to be reinforcing bad math. Station 13. Well, let's take a look. Here I've got some cases where the denominator is the same in each problem. And to me, this is saying partial fraction decomposition. Well, in fact, ooh, is it? No, I don't think it is. I until I moved that 4 out, I thought I was doing partial fraction decomposition. And maybe we should do this one as partial fraction decomposition, but I don't feel like we need to. Um, yeah, let's try it both ways. Okay, so this is going to be 1 over x minus 1 squared is a over x minus 1 plus b over x minus 1 squared. I multiply everywhere by the least common denominator. That's this. I end up with 1 equals a x minus 1 plus b. Okay. So if I make x equal to 0, I'm sorry, x equal to 1, that's going to be 0, and I get b equals 1. And if I plug in x equals 2, so what do I get? 2 minus 1 is 1. 1 times a is a. I get 1 equals a plus b is 1. So a must be 0. Well, that's interesting. Okay, so that's not part of, ooh, and that just sort of brings me back to where I started. Well, that's very unfortunate. So partial fraction decomposition didn't really help me there. What would? Well, what if I thought about the problem this way? Oh, so it's a U set. So this integral becomes 4 u to the minus 2 times du. Okay, so what will I have here? 4 u to the minus 1. Let's see. I bring down the negative 1, I get positive 4, subtract 1, negative 2. Yeah, that looks good. And then I have to do that substitution. Don't remember that this is the u value here. So we've got negative 4 x minus 1 raised to the negative. And don't forget that c. Okay, is that station 13 part A? That's okay for station 13 part A. Yep, negative 4 over x minus 1. That's perfect. Two. Okay, so I think I'm going to do partial fraction decomposition here. A over x minus 1, b over x minus 1 squared. So I'm going to get x equals a x minus 1 plus b. If I make x equal to 1, this goes away, and b equals 1. If I plug in, let's do 2. If I plug a 2 in here, 2 minus 1 is 1, 1 times a is a plus b equals 2. And my b value is 1. So now I can take this integral, which I was having difficulty with, and I can turn it into 2 separate learning experiences. Okay, I think that's good. So, yes, that is going to be ln. But over here, no. This is going to be 1 over x plus 1 to the minus 1. Oh, positive. If I move it up to the top, then it's x plus 1 to the minus 2. No. Okay. Yep. And yep. Okay, number 3. 3 on station 13. 2x minus 3 over x squared minus 2x plus 1 dx. Well, I think this is a u sub where u is the whole denominator. And look what du is. It's feeling pretty close. Especially if I copied the problem down properly. Okay, so this is going to become the integral of 1 over u times du. There we go. So ln of u and don't forget the plus c. All right, that was 13. How many are there, you say? Well, I have 18. So a few more. Station 14. 1. Okay, so do you recognize that one? You really need to recognize that one. This is the station of ones you're supposed to recognize. And what you're supposed to recognize here is you need the power reducing identity. And so we end up with 1/2 Okay. Anyone else want to move this 1/2 out? Oh, I sure did. So I'm done. Okay. Antiderivative of 1 is x. Antiderivative of negative cosine is negative sine. So if I take the derivative of this, negative cosine, take the derivative of the inside function, uh-oh, I need over 2. All right, so number 1, that's going to be all about knowing your power reducing identity. Whereas tangent squared x dx, this one is going to be all about knowing your Pythagorean identities. Whose derivative is that? That's tangent's derivative. The antiderivative of 1 is x, and don't forget the plus c. And that's nifty if I remember my Pythagorean identity. How about this one? Secant squared x dx. Yeah, we just did that. That's tan x plus c. For integral of tangent x. Oh yeah. Remember when we did this with u subs? Sine over cosine. Because here, nothing, but here, I see a function and someone else's derivative. So if u equals cosine of x, du is negative sine x dx. And since we have a sine d something, so we can replace all of that with negative du. And the stuff on the bottom is u. So 1 over u times negative u. What's my antiderivative here? Well, this is u to the minus 1/2 with that minus in front. So I want to say u to the 1/2. Bring down that 1/2, I have a 1/2, but no, it should have a negative 1. So, what if I have a negative 2 here? Bring down that 1/2, negative 2 times 1. Yep, that's good. Do we need anything else here? Yes, we need the plus c, and we need to rewrite this so that we have x's. So, negative 2 square root cosine x plus c. Okay, and then the last one on station 14. Tangent inverse of x dx. All right. So what I know about tangent inverse is x squared plus 1 dx. That leaves only a 1 here, or 1x here. So let's multiply those together. Subtract the integral of x over x squared plus 1 dx. Okay. Yes, u sub u equals x squared plus 1. Du is 2x dx. That's close. I have x dx, not 2. So let's divide by 2 on both sides. Okay, so this integral can then be rewritten as 1 over u. And I'm replacing here x dx with d over 2. So we've got minus du over 2. Oh, that's a start. Du. And so there it is. And no need for brackets because this will never be 0. Ooh, station 15 has more of the same. Let's take a look. Station 15. And number 1, cosine inverse. Well, this is that by parts thing. Well, we put the thing we know how to take the derivative of. And 1 dx. So we're going to have x cosine inverse x minus the integral of negative x square root 1 minus x squared. Okay, so I want to take do u sub here. That looks good because I have negative x dx. So du over 2 is all that stuff. Now here, 1 minus x squared, we said that was u. So I have 1 cosine inverse x minus integral 1 over square root of u over 2. Alrighty. Well, that's u to the minus 1/2. And this is 1/2 out of that. So 1/2 goes up there. Bring that down, just like that. This is already done. And don't forget the plus c. And don't forget to replace your u back, right? So x cosine inverse x minus square root of minus x squared plus c. Great. There's number 1. Number 2. Integral of ln of x dx. Hey, will you do that one? I'm just going to grab some water. I'll be right back. I recommend by parts on that one. Well, how'd it go? Did you get this? And there's our antiderivative. Okay. This next one. So multiple choice on the AP exam. So that's an exponential function. That's like 2 to the x. This is a power function, like x to the third. So keep that in mind when you do this. The antiderivative here, pi to the x ln pi. No, Mr. Kukla. Come on. This is the derivative of pi to the x. We need the antiderivative. So ln of pi on the bottom. Why? Well, think about this. Think about this as 1 over ln of pi times pi to the x. And now I want to take the derivative of that. Well, the derivative of e to the is e to the, so pi to the is going to be pi to the. But don't forget to do the ln of pi. This cancels that, and there it is. Okay, so that one minus here, pi x to the pi minus 1 plus c. No, Mr. Kukla, you did it again. That's the derivative. Yeah, no derivative. We want pi plus 1 over pi plus 1. So now if I took the derivative of this, and that came down with cancel, I just have that minus. Very good. That's a great test question. Okay, please pay attention to whether you're going backwards or forwards in these problems. Okay, number 4, e to the minus 3x sine 2x dx. Oh, that's that by parts one, that both of them spin forever, so you have to go around twice using by parts. Okay. Hey, so the antiderivative of that, e to the minus 3x over 3. Because if you take the derivative, and there's a 3 that's going to come down. I'm at a 3 here, so there must have been something present on the original function. In fact, I need that as well. All right, so what do we have? We have the integral e to the negative 3x sine 2x dx equals negative e to the minus x sine 2x, that's this times this, minus the integral negative e to the negative 3x over 3 times 2 cosine 2x dx. Now there are a bunch of constants here, so let's pull that out, and let's pull that out and make this a little tighter, and maybe a negative times a negative for a positive. So I'm looking at e to the minus 3x sine 2x dx equals negative e to the minus x sine 2x plus 2 thirds e to the minus 3x cosine 2x dx. Okay, getting there. But it looks like I have to do by parts a second time, and that's of course always true with these spinning problems. So I'm integrating this, and we have trig up here. So cosine 2x is going to be minus sine 2x times the derivative of the inside dx. And here we have e to the minus 3x. And this will be e to the minus 3x over 3. All right, so where does that take us? Well, the integral e to the minus 3x sine 2x dx equals negative e to the negative 3x sine 2x plus 2 thirds. And now the antiderivative here, yeah, that's this one, is going to be cosine 2x over 3 e to the minus 3x minus the integral of this times this. Oh, no. There's definitely a sign mistake somewhere. Yep, sorry, I'm gonna do it again. Really, you can't, like, rush perfection. Just take your time and do it right. So, integral e to the minus 3x sine 2x equals this times this. So we have e to the negative 3x sine 2x minus the integral 2 thirds e to the minus 3x cosine 2x dx. Okay. I think I like that. I like that so far. Now I'm going to do by parts a second time. So we've got e minus 3x, 3 sine 2x minus 2/3. This times this. E minus 3x over 3 cosine 2x minus the integral of this times this. And so that's going to be minus 2/3 e to the minus 3x, 2x dx, and see that minus right there? Well, that minus times that minus that minus is that minus. Never mind. So we've got this minus, and this minus, and this minus. Negative times a negative times a negative is going to be a negative. So let's write this like that. Okay. I distributed that. I think I did. Oh, there's a 2 and a 3. No, I did not. I'm just running out of space here in some really uncomfortable ways with this problem. So much easier on a full-size classroom whiteboard. So that's going to be minus 2/3 e to the minus 3x sine 2x. And this is that. And there's the 2, and there's the 3. But this is an integral. Wow, tough time today. So we've now got the integral of e to the minus 3x sine 2x dx equals e to the minus 3x over 3 sine 2x minus 2/3 times this one, e to the minus 3x over 3 cosine 2x, and now we have minus 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 the integral of e to the minus 3x times sine 2x dx, but there's a 2/3. Okay, so minus times minus times minus is minus, and we have a 2/3 times a 2/3, which is going to be a minus 4/9. Whoa! All right. Now, I stopped the first time because I didn't have a minus here. So now, this e to the minus 3x sine 2x is that. So I'm going to add 4/9 e to the minus 3x sine 2x dx to both sides. And so that's going to be 9/9 plus 4/9, 13/9 e to the minus 3x sine 2x dx equals, and what am I left with here? I'm going to have e to the minus 3x over 3 times sine 2x minus 2/3 cosine 2x plus c. Not quite. We don't want 13/9 over there. So we're going to multiply both sides by the reciprocal. 9 over 13. 9 over 13. To all of that stuff. And so we end up with 3 over 13. No, you don't really have to worry about that because, you know, it's just a constant. Doesn't matter if it's 9/13 times that. We won't know anything until we plug a value in, and this isn't one of those problems. Okay. All right, and then number 5. So we've got cotangent x dx. Well, that's cosine x over sine x. And if u equals sine x, then du will be cosine x dx. So this can become the integral of 1 over u du, and we know that's going to be ln of u plus c, or ln of sine u is that. Thank you. Plus c. There's my answer. Okay, next. Oh, that was it. Okay, there's station 15. Station 16. Wow, so many things look alike. Number 1, the integral of y squared plus 8 dy. Now, this is a u sub, where u equals y squared plus 8. And so du will be 2y dy. More du over 2 is y dy. And here's my y dy. So this can be 1 over u times du over 2, or 1/2 integral 1 over u du, which is 1/2 ln of u plus c. Hey, don't forget to plug that back in. 1/2 ln y squared plus 8 plus c. And there's problem number 1. Problem number 2, integral y squared plus 8 dy. So do you remember talking about improper integrals? When the degrees on the top and bottom are the same, what is it that I'm supposed to do? No, it's not a horizontal asymptote. I'm supposed to do long division. So this can be rewritten as 1 minus 8 over y squared plus 8. Yeah, okay. That's why we did this long division. One and once. We subtracted, we get that negative 8. It's going to be our remainder over our divisor. Yeah, that's it. Antiderivative of 1. Now here, does that look familiar? Does that look like you should know how to do that antiderivative? I'm hoping so. I would love it if you said, hey, that's almost inverse tangent. If only I had a 1 here. Okay, that's looking good. So then we've got y minus 8 integral 1 over y squared over 8 plus 1. No, those cancel. There we go. Okay, now what about this? Well, if our u is y over the square root of 8, I can rewrite this integral then as y minus 1 over u squared plus 1 du. So y minus tangent inverse of u, and we know that u is this stuff, so y minus tangent inverse y over square root of 8. Don't forget the plus c. Wow, so improper integrals, those are the ones where the degree on top and the degree on the bottom are either the same or the degree on top is bigger. In those cases, I would use long division. So what if I have just 1 over y squared plus 8? Well, this is, we saw part of this in the last problem. after we did our long division, and this was going to turn out to be an inverse tangent. We're going to divide by 8 and multiply by 8. 1/8, 1 over and if u is y over square root of 8, are these 8s? Yes, these are 8s. Then du is 1 over square root of 8 dy. Root 8 du is dy. Okay, so this is going to be 1/8 times 1 over u squared plus 1 root 8 du. Well, that can come out. This is going to be 1 over square root of 8 tangent inverse of u plus c. And there's my u. So it looks like my final answer, 1 over root 8 tangent inverse y over root 8 plus c. I don't know, I feel pretty good about that one, but you might want to do it again and check. 4. Integral y to the third over y squared minus 4 dy. Degree of the top greater than or equal to the degree of the bottom. We need to use long division. Okay, so I'm going to multiply by y. Y to the third minus 4y and subtract. And so I get 4y as my remainder. So this thing that I couldn't integrate can become y plus 4y over y squared minus 4 dy. Well, that's great. I feel like I can handle both of those pieces. Antiderivative of y, no problems. That's y squared over 2. What about here? Do you see the u sub? So u over 2 equals y dy. There's my y dy. So I'm going to have the integral of 1 over u. No, it's 4 over u du over 2. Well, that cancels there, and that cancels there. Oh, no, there was a sign. What was it? It was a plus sign. There we go. Okay, so can we tidy this up a little? Y squared over 2 plus the integral of 2 over y. That's supposed to be a u. Yeah, sorry, can't do it again. Long division. Y and subtract. So this is equal to the integral of y plus 4y over y squared minus 4 dy. All right. Now I want to kind of do it as partial fraction decomposition. And we haven't done one of those in a little while. I wonder if I should try one of those now with this station problem number 4. We could do either. think I just want to do the u sub because, this y squared is going to be 2y. So I've got the integral of y plus if u equals y squared minus 4, du over 2 is y dy. So I've got that 4, and that u, and that du over 2. I think that works. This 4 is here. This is u dy, y dy is du over 2. Oh, that's good. This with this. So I get y squared over 2 plus the integral 2 over u du, which is y squared over 2 plus 2 ln of u plus c. And there's our u to plug back in. So y squared over 2 plus 2 ln y squared minus 4 plus c. I think that's good. Yep, that's nice. Did you really want me to do it with partial fraction decomposition? Okay. So we still have to do the long division. We still have to do the long division. Do you still have to? Yes, you still have, because this is an improper one. Okay. So we had y plus 4y over y squared minus 4. And that's what we're integrating. Okay, so this is still going to be y squared over 2. But here, for y, split this up, y minus 2, y plus 2. I multiply everywhere by my least common denominator. Give me 4y, a, y plus 2, plus b, y minus 2. So when y equals negative 2, we have negative 8. Negative 2 plus 2 is 0. This is minus 4b. So b equals 2. And if we plug in y equals 2, this one goes away. We get 4a equals, we plugged in at 2, 8. And so a equals 2. Right. So I guess now that we know that a and b are 2, we can say plus the integral of 2 over y minus 2 plus 2 over y plus 2 dy. And so if we pull out those 2's, I'm going to see 2 ln y minus 2 plus ln y plus 2. Don't forget the plus c. And we've got a y squared over 2 here. This 2 has to go to both of these, so I'm thinking about that. Look, 2 logs joined with addition. Hey, wasn't there something I could do about that? Like combine them into one log with multiplication? And so that's going to be the ln of y squared minus 4. Don't forget the plus c. There's a 2 out in front, and a y squared over 2. And there we have it. Okay. And that was 4. What about 5? The integral for y plus 8 dy. Well, let's start by doing that. And now, how about u equals y plus 8? So du is dy. So this integral can now be 1 over u du, or ln of u plus c, and do that back substitution, perf y plus 8, and don't lose your c. Nice, that wasn't so bad. And this last one, integral for y plus 8 squared dy. I'll pull out the constant and rewrite this with a negative exponent. Whose derivative am I? Well, you know, if you're not sure, remember, you can always say that this equals u. And so that dy would be du. So this now becomes 4 times the integral of u to the minus 2 du. Okay, so antiderivative here. Well, not quite, because when we bring down that minus 1, I don't see any negative here. So that is what I'm looking for. And we subtracted 1. Okay. We have that 4. That's this minus, because I'm doing an antiderivative, plus c. And don't forget we have this u, so we've got negative 4 over y plus 8 plus c. So if I take the derivative of this, I should be able to get back to my original problem, which is this. All right, well, that was station 16. Only 2 more to go. We're looking for the particular solution to this differential equation, x squared, y minus 1. Okay. We're also asked to write the equation of the tangent line at that given point. Oh, that's very exciting. But step 1 here, or step A, is sketch a slope field. Okay, if I plug x equal to 0 in, dy dx is 0. If I plug y equals 1 in, 1 minus 1 is 0, 0 times stuff, I get a 0 slope again. Okay, what about down here? What about y equals 0? Well, I'm going to have negative 1 times the x value. That's going to be negative 1. And I'm going to have negative 1 times 4. Oh. And if I plug in 1, negative 1. 1, negative 1. It's going to be negative 2. 2, negative 2. No, it's negative 2 here. That's negative 3, 4, negative 12. Oh my gosh, that's so steep. And that was that one there. That's the negative 12. Okay. Here, 1, negative 2. Negative 3. And 2, negative 1. Minus 2 times 4 times 8. Okay. Negative 1, 0. No. X is negative 1. So it's 1 times negative 1 is negative 1. And if I plug in negative 2, 0, I get negative 4. Negative 1, negative 1. So that's going to be negative 1, negative 1. That's going to be 2, negative 2. And over here, we have negative 1, negative 2. That's negative 3. Negative 2, negative 2. Negative 3 times 4 is negative 12. Okay. And stop. Okay. Yeah. So, I'm getting a little concerned. I think I'm going to skip finishing that one. I'm going to write the solution here and then the tangent line. Okay, so we've got this dy dx. squared times y minus 1. And we were given the ordered pair 0, 3. So dy equals x squared minus 1 dy. No, dx. I want to get rid of this y stuff. And now when I integrate, I have ln of y minus 1 equals x to the third over 3. And don't forget the plus c. Okay, you could plug in your initial condition now, but I really don't want to play with that ln. So I'm going to take this further. I'm going to exponentiate. Notice the c is up here with the exponential power. It's not on the same line down here with the e. Make sure that stays true for you. And then what can I do? Well, I've got absolute y minus 1. And here, because of that plus sign, I can write e to the c times e to the x over 3. To get rid of these absolute value bars, I need to introduce plus or minus e to the c. And let's take this and say that plus or minus e to the c is b. So I've got y minus 1 equals b, e raised to the x to the third over 3. Great. Now I feel like I could almost be ready to use that initial condition, 0 to 3. That's an x value, that's a y value. 3 equals b times 0 divided by 3 is 0. E to the 0 is 1. And so I end up with b equals 2. Okay, well, let's plug that in. And there's my model. Now, how do I write the equation of the line tangent to this curve at the point 0, 3? Well, I need a point, but I also need a slope. And in our class, a synonym for slope is derivative. So what was our derivative here? Our derivative here was dy dx is equal to x squared y minus 1. So let's plug our ordered pair in. Uh-oh. I get a slope of 0. So y minus 3 is 0, x minus 0. And so y equals 3 is the equation of that tangent line. Nice. Okay, station 18. Goodness me, isn't that more of the same? Cool. It sure is. I think I'll solve that differential equation for you. I'm definitely skipping the slope field. I'm pretty sure you can all do slope fields now. dy dx, negative x, y squared over 2. Okay, we want to do separation of variables. So we're going to have dy over y squared is negative 1/2 x dx. So this, you probably want to do that as y to the minus 2 dy. Just saying. It's going to be minus y to the minus 1. And over here, negative 1/2 x squared. Did I need that? Yes, because there's a 1/2 there. Okay, so plus c. Got negative 1 over y equals negative 1/4 x squared plus c. I like getting it in y equals form first. But I guess we could do this here if I plug in a 2. And if I plug in a negative 1. So that's going to lead me to negative 1/2 equals negative 1/4 plus c. And so I get negative 1/4 equals c. Okay. But you see, the equation isn't solved for y equals yet. Right now we've just got this. If I multiply everywhere by negative, and it's going to be x squared plus 1 over 4 over y. Okay, so if I flip both of these, I'm going to end up with y equals 4 over x squared plus 1. And I don't have a c because I already solved for it. Yeah, that must be my equation there. There's part B at station 18. And finally, we want the equation of the line tangent at negative 1, 2 to this function. Well, I have the point already, but I still need the slope. So remember, synonym for slope in our class is derivative. And so that's going to be minus 1, 2 squared over 2. Well, that's going to be 4 over 2 is 2. And so now y minus 2 is 2x plus 1. And I would probably stop there. But you could take it further and say 2x plus 4. All right, well, that was a lot of stations. I hope that helps. I hope the next test goes well. And I look forward to hearing from you soon. All right, take care, everyone.